axiomatization of a graph isomorphism via graph rewriting in Coq.
Yeah, okay, so welcome to my talk. This is joint work with Damien from the ENS in Lyon. And I guess I should start by explaining to you what we actually mean by axiomatizing graph isomorphism, because I mean that's not something that people in this audience would normally do. And so what we mean by this is formalizing or proving a statement of this shape, where you have a language of terms over some signature. In our particular case, the signature is one which has two binary operations, two unary operations, and a constant over some collection of letters taken from some alphabet. And then you have a function that interprets terms as graphs. And you have an equivalent that you axiomatize on those terms. And you want to prove that two terms are equivalent if and only if they describe isomorphic graphs. So here we have the axiomatized equivalence, and here we have graph isomorphism. So that's the theorem we're after. And for this to actually make any sense, I probably should explain how we interpret terms as graphs. And in fact, graphs form an algebra over that same signature. So what we need to do is interpret the term operations on graphs. And well, the kind of graphs that we're dealing with in this kind of theorem is we're talking about graphs which are directed labeled multigraphs, where you have two distinguished vertices, which we call input and output. And the input is sort of marked by an ingoing arrow, and the output is marked by an outgoing arrow. And so as an example how this interpretation of terms as graphs works, I want to show you how to sort of construct this graph as the graph of a term, namely that is this term over here. And well, the first thing you do is you replace all the term operations by graph operations and the letters by atomic graphs, where an atomic graph is just a graph that has two vertices and an edge labeled with that letter. And well, now we have to sort of evaluate these operations. And let me first just put the atoms that are occurring in this term into the empty space. And then sort of we start from the inside out evaluating the operations. So the first is this domain operation, which just relocates the output to the input. So afterwards, this graph looks like this. And then you have here you have a dot, which is the sequential composition, which just means we identify the output of the first argument with the input of the second. So that means here a vertex actually vanishes because you're smashing those two vertices. And then for converse, you swap the role of input and output. So now you essentially have an atom where the arrow goes the wrong way or the other way. And then you have another sequential composition. And for parallel composition, rather than identifying input and output, well, you identify the respective inputs and outputs. And then this shows that, we have constructed this graph, which indeed is the graph I wanted to construct. And so this is this half, and the other half of the statement is, it's just 11 equational axioms. I don't want to go into any details here because, I just want to show them here for completeness. There's really nothing spectacular going on. It's just a bunch of equations. Okay, so the question is, how does one go about proving this, in fact? So, and why would we actually want to prove this? So the first time this theorem, this was proved on paper by Damien and a former colleague of mine. It was published at MFCS 2017. They use a slightly different term language, but for the purpose of this talk, I'll just gloss over this. And they actually prove two things. So the first thing is, the question is, which kind of graphs can actually be described? Because you can't describe all graphs by this. And for those who know, this is exactly the graphs of trees at most 2. So it's a fairly restricted class of graphs. And then they go on and prove soundness and completeness of an axiomatization for this particular class of graphs. And in fact, this was used as a building block to settle the completeness, to show completeness and decidability of a theory called allegories. And that actually was a problem that was open for a number of years. It's probably not the most investigated problem, but that's sort of the problem that motivated this whole endeavor. And sort of in parallel to this, Damien, and our shared intern, we started formalizing this paper, and we got to the point where we had sort of formalized this first half. And this required quite a lot of graph theory in the background, particularly a theory about trees and minors, these kinds of things. And then we realized that, well, once we had actually submitted this, that for the completeness direction, there's a much easier proof that does not require any graph theory and just uses a confluent graph rewrite system. So this we published at MFCS 2018, and in this talk, we talk about the formalization of that paper, of the main part of that paper. And sort of in parallel, we've been working on a journal version of this paper. So this has a sort of a cleaned up theory of minors trees, and it also includes the soundness direction of the statement I had. So I will not talk about soundness, I'll only talk about the completeness direction here. So sort of to give an idea of the completeness proof in a nutshell on one slide, is what we do is we generalize the problem from the letter label graphs that I had on the slide back to graphs where both vertices and edges are labeled with terms. And then we have well, terms over that exact same signature. And then we have a rewrite relation on those term-labeled graphs. And then actually you need two main properties. One is reducibility. This says if you start from the graph of a term, the rewrite system actually allows you to reduce that term to an atomic graph that is labeled with that term. And so this is, I'm glossing over a little details here. And the other thing is you show that it is that this rewrite system is confluent modulo both graph isomorphism and equivalence on the labels. This is a rather lax notion of equivalence of graphs. And as a result, what you get is, well, if you have two terms which yield isomorphic graphs, then these are essentially the same graph, and the rewrite system will reduce both, well, to the graph labeled with U and the graph labeled with V. And since you have confluence, the only way to merge them is by actually exhibiting that the labels are the same, because both of them are normal with respect to rewriting. So that is sort of the idea how you get this in a nutshell. And so I don't want to spend too much time talking about the rewrite system, just give you some rough ideas here, because I also want to talk about the formalization. So the idea is that, as I said, the labels are terms, and terms describe graphs. So in particular, the edge labels describe graphs which have distinct input and output, and the vertex labels describe graphs which have shared input and output. So morally, you could just replace every edge by the graph it describes, or described by its label, and you can replace every vertex by the graph described by its label. And the rewrite system is designed such that it preserves this expansion. So this is similar to the state removal method for to get regular expressions for NFAs, where you generalize from letters to regular expressions, and then you just modify the automaton while preserving the language. Here we preserve the expansion. So that's sort of the idea behind this rewrite system. Okay, so much about the mathematical side of it. Let me talk a little bit about why this was actually quite tricky to formalize. So and the first thing I want to talk about is, of course, I mean, if you're doing something graphs, yes, you need to have a representation of graphs. Yeah, I see the raised eyebrow over there. And so the main representation we use is, well, a fairly naive one, where you have the tuple here, and you have a finite type of vertices, as like finite types as provided by MathComp. So we actually do build on MathComp. And you have a finite type of edges, and then you have a function giving for every edge its point, so its source and its target. And then vertex labeling, and so on and so on. And the nice thing about this representation is that the representation invariance, such as that every edge starts and ends at a vertex, is actually enforced by type checking. The not so nice, well, the double-edged sword part of this representation is that, as Abhishek just said, operations on graphs actually change the type of the underlying type of vertices. So if you add a vertex, then you just have a vertex type B plus unit, because you need an extra element in that type. However, you can do something fairly nice with this representation, and that is, well, as it comes to representing the rewrite rules. So one thing you can do is, well, if you think about, that's one of the rules I had on the slide back, where you just have a degree 1 vertex that you sort of pull in and update the vertices. Then you can sort of formalize this as by making explicit the part of the graph that doesn't change. This is what I call the additive representation of this rewrite rule. You say G with an extra vertex and an extra edge reduces to G with an updated label. And this means you have no side condition whatsoever in the rule. And this works really well for showing this reducibility statement. However, on the flip side, because you have here some complex expression, sort of a priori steps are not preserved under graph isomorphism, and this really makes proving confluence hard. I mean, okay, this is terminating, we only need local confluence, but it's still hard. And so why this is really hard, I mean, there's a whole page in the paper dedicated to explaining why this becomes hard, so I can't elaborate on this. But so what we need is, we actually, for the purpose of local confluence, we need a second representation of the rewrite system. This is what I call the subtractive representation, where you always have a graph on the left, like just a single variable, and then you say you go from G to G, where you removed some stuff and updated stuff, something like that. And well, then you of course need some side conditions. You actually need quite a few side conditions, so this is sort of the bad part. But the good part is that for this representation, you can show that steps are preserved under isomorphism, and hence you can do the usual local confluence argument as you would expect. But if you do this on the representation of graphs on the backside, where removing a vertex means actually forming a sigma type on the vertices, if you do a bunch of steps, you have nested sigma types, and this is kind of a bit like dependent types hell. So in fact, we use a second representation of graph things. And so there, instead of using like finite types of vertices, we use, we fix an a priori type of vertices and a type of edges, which are just copies of the natural numbers. And then the graph representation is just, well, graph has a finite set of vertices, so like this is finite sets as provided by MathComp again, over the a priori existing type of vertices. And this means, well, two things. One, modifying a graph doesn't actually change the edge or vertex type, because there is only one type. But on the other side, in this representation, you need well-formedness conditions, because now you need to totalize this point function. And you have to, whenever you modify it, you have to check that still every edge of the graph actually has its source and target in the graph. So this is no free lunch. And so the overall proof structure is as follows. So what we do is, well, we prove the reducibility statement for the additive representation of the rewrite system in the setting of packaged or dependently typed graphs. Then we prove the local confluence statement on the subtractive representation of the rewrite system on open or simply typed graphs. And then we transfer this statement to the setting of to the additive rewrite system over packaged graphs. And well, the takeaway here is that, well, for graphs, more than anything else, the right representation of any given concept depends on what you want to prove about it. And in this case, we actually had the proof nicely factored into two parts, and they just had contradictory requirements on what you need as reasoning principles on the graphs. So at some point, you just have to face it that, well, you need two representations, and you need sort of the infrastructure for transferring, but now we know how to do this. So now we have two representations, and we can work with it. It should become easier if you run into this again. So I'm starting to run out of time, so I'll just wrap up and make a few concluding remarks. So the total size of the formal development, the part that I talked about here, is about 5,000 lines of code, and it's not factors roughly 2 to 3 between specification and proof. So we're kind of thorough in having many small lemmas in the typical MathComp style. And well, as one would expect, the biggest individual lemma is the actual local confluence proof, because and I only showed you 3 rules, but there's actually 5 of them. So even after symmetry breaking, you have 15 cases. And moreover, what I didn't tell you is that it's not just up to isomorphism and equivalence on labels, but actually also all the rules are mapped up to flipping edges, which means that we have, well, this edge flipping you do without loss of generality reasoning. You have 13 instances of without loss of generality reasoning within a single lemma. But still, I mean, 500 lines, I mean, that's the main thing. We published this proof at MFCS a year and a half ago, And if there's any place in this paper where I think like, there might be a hole in our proofs, I mean, there would have been this, and there wasn't any. So it is good to know that the paper we published a year and a half ago didn't have any holes. Well, and the other thing is that, well, yes, this transfer comes at a cost, but I mean, we're transferring both the data structure and the representation of the read-write system. So this is not like unexpected that you need to pay here a bit. Okay, so to wrap up, so the result we formalized in COC with MathComp is soundness and completeness of these 2p-DOM algebras. And well, if you've paid attention, you notice that the term language I showed you can only describe connected graphs, because there was nothing that would introduce a disconnected graph. The result actually in the 2p algebras I mentioned in the very first paper actually talks about possibly disconnected graph with a slightly different syntax. And this extends all very smoothly, and we just haven't formalized this yet. So this is one thing. And the other thing is that, well, in fact, the graphs actually do form the free algebra. And for this, we would like to establish this isomorphism of algebras. But for this, you need actually the function that takes a graph and constructs a term out of it. And we have such a function. That was what we formalized in the ITP paper. But that is really outrageously complicated. And we would like to use the rewrite system to actually extract terms. But for this, you have to prove that it doesn't get stuck on term graphs. OK, so the last slide, I mean, we have done quite a few things. And so by now, we have built a relatively large library for doing graph theory reasoning in COC. And so this is the part I talked about here. And in fact, local conference is the only place where we actually need a simply typed graph. Everything else works really nicely with dependently typed graphs. And yeah, if there's, of course, there's many things you would want to add to this library. So if you want to do something, talk to me and stay tuned, because we're currently working on a GitHub release and open packages, but there's just some issues that need to be sorted out how to do this in a clean manner. So this might take a few words. And well, thank you.
We have time for a few very quick questions.
My memory is failing me, but yesterday there was a talk where some concept was presented in 3 or 4 different forms, and univalence was used to reconcile them. Would you have a use for univalence in your case?
Probably. I thought about mentioning this, but then I thought I have so much on the slides anyways. So I suppose having univalence would be really nice. On the other hand, I would like to have, well, univalent COC with MathComp on top, because I mean, I'm ditching MathComp for univalence. Whether that works well, I don't think so. So might take a while until you can really profit.
OK, let's thank our speaker again.